So, like I said, today we're going to be introducing the idea of limits, right? And limits are fundamental to, like, understanding calculus, too, okay? Like, every major topic that you're going to learn about in calculus will result from limits, okay? There's kind of two main branches, differential calculus and integral calculus, okay? You learn differential first, and then integral is like reverse differentiation, or like the inverse of differentiation kind of thing. Just like you do with everything other thing you learn in math. You learn one operation, and then you learn the inverse of it, the reverse kind of thing. So anyway, but limits are fundamental to both of those things, okay? And there's this concept, okay? We're going to start out, you know, pretty easy, but I will say also limits, this is more conceptual, okay, than like some of the stuff that we do. Like, you know, sometimes math is just like learn how to do the thing and you just do the thing, right? But limits are a little more conceptual, a little more like thinking and stuff like that. AB, BC students, you know, and AB students in calculus tend to find this test when you do test on limits and you do it early on, tend to find this test, you know, difficult, you know, rather difficult, even though it's like one of the earlier topics that you discuss, okay? So again, not trying to like scare you, just trying to like forewarn you, okay? This can be tricky, and so if you find it tricky for yourself, don't worry, you're in good company, but you know, make sure you get it figured out before test or quiz time, okay? So, and hopefully I'll do a good enough job so that you can understand it here too. So 2x squared minus 5x plus 3 all over x minus 1. So we're going to consider that very function that we discussed in the warm-up, all right, whose, you know, value we could find at pretty much every point except at 1, right? And at 1, we know that we get that 0 over 0 indeterminate form, yet we're able to also cancel things out there, right? Grant was able to do the division there, and then when we plugged 1 in, there was no problem. We got a value. So, like, what should we say there? Should we say that there's nothing going, like, what, you know, with indeterminate form, it's kind of like, you know, nebulous. What does that mean? But, like, we know that there can be a 1 value there, so what's happening? So, the graph of this, okay, question, Jeff?
Could a limit also be called an asymptote? Is it the same thing?
They are related, yes. They are related, yes. Okay, but not every limit will, you know, we can use limits to evaluate asymptotes and stuff like that, but
so an
not all of them.
asymptote is a special type of limit that has values on both sides?
It doesn't always have values on both sides, but and I would say an asymptote is something where the as you approach it from either side, the function value goes to infinity. Or negative infinity, yeah. Or negative infinity, yeah. Mm-hmm. Yeah. Mm-hmm. Yep. Okay, so let's graph this function, see what's going on here. All right, so I'm going to type this in my calculator. So, and I suggest you guys do too, because we're going to be using this function. So I know you know, maybe you just want to see the picture, but no, go ahead, type it in your calculator here. So I'll just, you know, this right here.
I don't think I've ever graphed anything with this new calculator.
All right, well, we're breaking her in today then. All right, so go ahead, type that in your graphing calculators. Okay, and I'll give you guys a chance to type it in before I throw mine up there. And again, we're graphing g of x here in your graphing calculator. And this is another thing too. If you're not super familiar with your graphing calculator, if you're not very comfortable with using it, I've had students say that they hate their graphing calculator before, you know, because they like don't like how you type stuff in. And I get it. You guys are used to like your smartphones and stuff like that, and those are like maybe much more intuitive to you. And these calculators, they haven't changed how you enter stuff since at least the mid-90s. So 20 years they haven't changed like the system, the operating system for it or whatever. It's the same method, so it's, you know, it's like, I understand, but you do need to learn how to use it, because again, if you're planning on taking calculus or if you're planning on taking statistics, you're going to be using this pretty intensely, and so it's important that you can utilize this tool, even though it is kind of old in its formatting and stuff. All right, so hopefully you've had enough time in my delay there. All right, so you got a graph like that? If you do, you typed it in wrong. Okay, if that's what you got, you typed your graph wrong. All right, so if you do have something like that, you forgot to put parentheses around your numerator, which is important. Okay.
Put parentheses around my numerator.
And denominator? And if you do, then you'll get something that looks like this. Okay.
And the
Good.
denominator. I
Good.
didn't know I had to do it around the denominator.
Yes, it's also important around the denominator too. Yep, otherwise you'll get the wrong picture. Okay, you get the wrong picture.
Well, what was that picture though? What was going on? That was weird.
What you typed in, so without, you didn't put parentheses around the denominator, you said, Jeff? Yeah. So what that was doing then, your calculator was following order of operations. Without parentheses around your denominator, it took the numerator, this 2x squared minus 5x plus 3, and divided it only by x, and then it subtracted 1 from that. So you want to divide it by the quantity x minus 1.
What was that like weird two-part graph with the linear and the...
I think mine was with no parentheses at all. I think that involves, like there's like an asymptote there and stuff like that, so.
So weird.
I know, we get some weird stuff here. But this one's not so weird. It's just a line. Okay?
Wait, mine's just a parabola.
Okay, well, I would say check what you typed into your function there. Okay?
3x
So,
cubed minus 5x plus 3 in parentheses. 5x squared. There it is. 2x squared.
you do have your glasses on, Jeff. You can't blame it on this time, all right? There it is. I'll zoom in some more there, though. Okay? It could be my bad handwriting.
There we go.
That does happen. All right. So, anyway, we're going to graph this thing, okay? And, let's see here. It looks like it goes through -3. Maybe I can use my, oh, right. I did that. 0, 1, 2, 3. Okay, so it looks like it goes through 0, -3, and hang on, 2, 1. Okay, something like that. Now, that at 1, if I go to my graph here, if I do, so I don't know if you guys knew this, but if you press second trace, use the value command, you can like put in x values and then it will spit out like what the corresponding y value is. So for example, if I typed in 1, okay, it gives me a y value of blank. Okay? So again, second trace, if you use the value command, which is the calculate menu, right? The calculate menu. If you press 1, okay, for your x and hit enter, it gives you a y value of blank, which makes sense because what did we already determine happens at 1? 0 over 0 in determinate form. Okay? So our sketch then at 1 is going to have, well, a hole in it. Okay? So something like that.
So it's a point of discontinuity.
Yes, a point of discontinuity, okay? I think we'll talk about this later as a removable discontinuity, right? Okay, so, but of course, we already kind of saw, but that indeterminate form, man, it really looks like there should be some sort of value we can come up with for this. So what we can do is, we'll ask the question, so what happens, okay, what happens as x approaches 1? Okay, so, oops, I'm off the screen. There we go. Okay, what happens as x approaches 1? So that's what we're going to do, because we know at 1 there's a problem, right? But maybe we can just like try and get like close to 1 and see if we can come up with, you know, some more information here. And so we'll do that via a table. Okay, in this case, oops, I would use g of x. Okay. And so we'll pick some values that are close to 1 on the left side of 1, and we'll pick some values that are close to 1 on the right side of 1. So I'm going to put 1 in like the middle of my table, okay, for this kind of like mystery value that we're trying to find here. All right, and I'm going to approach 1. So maybe I'll start with like 0. Okay, I'll start to the left of 1. Say again. Yes, exactly. So we'll get even closer then. We'll do like 0.9, and then we'll also do like 0.999 or something like that, okay? And then likewise, we'll approach 1 from the right-hand side. So I'll start really close, like 1.001, and then I'll kind of like move further away. Again, the idea being we're just kind of getting closer and closer to 1 as we move in from the left or from the right there. Okay, and then 2, I'll also put that on there too. Okay, so bless you. Again, we start further from 1, we start at 0, then we get really close, 0.9, then we get really close, 0.999. And then we start far away at 2, we get a little bit closer, 1.01, and we get really close at 1.001, right? So we want to evaluate these x values into our function. There's 6 x values we're going to evaluate here, okay? So I suggest you use your table, okay, in the graphing calculator. Now, if you have not messed with your table setup before, it's going to look something like this, okay? If you haven't messed with your table setup prior to this, and I forget if we have or not in this class, but we have? We have not? Okay. So it would look something like this. And this is nice. Yes, exactly. We'll get to that. So this is nice, but the problem is the calculator is automatically filling in the x values for us, and it's picking just like integer numbers, right? Bless you. How are we supposed to get 1.001 or 1.01? Well, Jeff's exactly right. Second window takes you to the table setup, okay? And what we're going to do here, we're not going to worry about where the table starts. We're not going to worry about the delta table, the change in the x value. We're going to go down to the independent variable and change it from automatically being filled in to have it ask us what values to plug in. So we'll go back to our table. It's now blank because it's waiting for us to plug in x values, and then it will put out the matching y value. Okay? And so we'll type in 0, and then 0.9, and then 0.999. If you want to, you can type in 1, but you know the calculator is going to give you an error there because that's an error. We'll do 1.001, 1.01, and 2. Okay? And so there, without having to repeatedly plug in the x values and type into our calculator, we can just use the table. So we get -3, -1.2, -1.002 from the left. From the right, we get -0.998, -0.98. I forgot the 0, but that's okay. And then 1. Okay? So, without simplifying our function, all right, as we approach 1 from values below 1, and as we approach 1 from values above 1, okay, what is our function approaching? -1, right? And that might not be that surprising to you, right? But this, again, remember, this is the unsimplified function here, right? In order to be able to get that -1 in the past, we had to simplify it and stuff like that. But here, we can still use our table and we get that. So g of 1 is indeterminate. But as x approaches 1, g of x moves arbitrarily close. I'll explain what that little phrase means. Arbitrarily close to the value of -1. Okay? So g of 1, indeterminate. We can't really say what happens exactly at 1. But we can say as x approaches 1 from either side, g of x gets closer and closer to that value of -1. So what do I mean by arbitrarily close? Well, so different people, right, or different, I don't know, whatever. Different entities might have different expectations about what it means to get close to a number, right? Some people might say, oh, that y value of 1 or that y value of -3, it's kind of close to -1 there, but it's not super close. And then, but as we get closer and closer here for the x values on either side, you can see that we get really, really close to -1. But some people here might still argue, yeah, Mr. Whitmire, it gets closer and closer to -1, but this is not -1 and this is not -1, right? They're both off by 2 thousandths, tens, hundredths. Yeah, they're both off by 2 thousandths, right? How can you say that's -1? That's still off by 2 thousandths, right? Well, we can get as close as you need to. The idea of arbitrarily close is that we can get as close as you need to be close to be convinced that it does go to -1. So if someone's like, Mr. Wood, I don't believe that this is close to -1 until you get within 1 billionth of -1. Well, we can do that. Okay, we would just put more 0.999s or put more 0.00000 and then 1 at the end. Okay, there. So we can get arbitrarily close. As close as you need to get to convince yourself that it's -1, we can get that close. That's what we mean by arbitrarily close. Okay. whatever arbitrary rule you came up with, that you need to be this close in order to say that it does, go to that. That's what we're going to do. We can do that. Okay, so here's a definition then. All right, if f of x, some generic function f of x, becomes arbitrarily close to a single number capital L as x approaches a number c. Okay, so there's two things happening here. X, our x value, is approaching a number c. Simultaneously to that, our y value, the function value, is approaching or becoming arbitrarily close to a number L. Okay? X, we are choosing to approach c, right? X is independent. We're choosing to have it approach c. And then we see what happens to f, the dependent, what happens dependently there as f approaches some number L potentially. Okay? So if f of x becomes arbitrarily close to a single number L as x is approaching a number c from either side, and the idea there from either side is that you can approach c from values that are less than c, and you can approach values that are from greater than c, right? Which is what we did here. We approached that 1 from values less than 1, and we approached 1 from values greater than 1. So you have to do it from both sides, or it has to agree with both sides. Then the limit of f of x as x approaches c is capital L. Okay? In shorthand, we can write the lim as x approaches c of f of x equals capital L. Okay? That is the shorthand way to write this. Okay? That's how you can write that out symbolically. Limit as x approaches c of f of x equals L. Okay? So, actually, questions up to this point? Questions on anything up to this point? Jeff, I saw your hand earlier. Did you have a question?
No, I actually get it.
Good. So far, so good. Jenna, you have a question?
I'm trying to read your writing. Is that x arrow c?
X arrow c. Yep. X arrow c. Yep. Okay. So, from our example, then, we can say the limit as x approaches. What was our x approaching in our example here? 1, as limit as x approaches 1 of our function. I'm actually going to write the function in. You can put g of x here, or you can put the actual function itself. Okay? The limit as x approaches 1 of this function is, and what did we determine the limit was based on the table there? Negative 1. Okay? So there is, practically speaking, how we could say all this in a simple statement. Okay?
It is a lot shorter.
It is a lot shorter, that's right. But it's important to understand what we're saying when we say it short like that. Okay? So, that's the idea. Let's try another one. So let's evaluate the limit as x approaches 0 of x over the square root of x plus 1 minus 1. Okay? And we'll do it by completing a table. Now, don't worry. All of calculus is not you filling in tables. Okay? We're going to learn other strategies. But this method is super important to you to have, because sometimes this is the only way that you'll be able to evaluate a limit. Okay? Is by using a table. Sometimes this is called the numeric method of evaluating a limit. Numeric method. Okay, and sometimes that's the best we can do. Okay? So I'm going to help you set up the table, and then I'm going to have you guys fill in the table yourselves. Okay?
Can you imagine how much math Isaac Newton had to do when he was first using his calculus after he made it?
Yeah,
I mean, that was back when there was no calculator.
Well, so my understanding with that is that the calculus when like initially developed with like Newton and Leibniz or something like that, they weren't super formal in how they developed it. So they didn't like necessarily prove things. They just started to see stuff happening and then develop some math around it. And it wasn't until later that they had to like make it more formal. Yeah. Because they were starting to like make errors and stuff like that, and they're like, "Ooh, we need to make this more formal." So I don't know the process of that, but yes, I agree. It's pretty intense calculations, But you can think about like people were using logarithms before there were calculators. People were evaluating trigonometry before there were calculators. So it's pretty impressive the kind of calculations that they were able to do. So anyway,
it's slow, but it works.
Yeah, and there's like other ways of doing things too, but. And some things we will never learn because it's lost to time.
Like the Antiquity theorem mechanism.
Yes, exactly. Yes. Yep. Never understand what that necessarily did or whatever, but it's pretty impressive. Anyway, so there's our limit. Again, we're approaching 0. I kind of filled this in here while I was talking, but the idea is, right, we want to approach 0 both from the left and from the right. To approach 0 from the left, that means we need to use negative numbers that are close to 0. So negative 0.1, negative 0.01, negative 0.001. Then from the right, we want to approach values that are greater than 0. So a positive 0.1, 0.01, 0.001. Okay? Developing this table can be tricky for students. Okay? It can be tricky. And I know you're just like, Mr. Wade, why don't we just skip to like the negative 0.001 and the positive 0.001? And yeah, you can when you're on your own and stuff like that, but you should be able to fill in the table. Just so you can kind of see the progression. As we move closer to 0, numbers get closer and closer to a particular value. So, Maddie G? Oh, I will come take a look at that in a second. So for the rest of you, though, go ahead, type, punch in this into your Y1, and then fill in, the values there using your table.
If it's just X on the numerator, you don't have to put parentheses around it.
Correct, you don't. Although, it's not a bad habit just to always put parentheses around your numerator and always put parentheses around your denominator. That way you're not going to forget it. Oh, I see the error is. So this right here, I guess in maybe your statistics class, you were using like your stat plots or something like that at some point. What? No? All right, maybe just the button got pressed. So anytime these are turned on, that means your calculator is going to try and plot data that you put in your list from your stat button there. So you can just toggle it off by hitting enter, and now if you type something, it should work out everything for you.
Okay.
So yes.
So I used to do this in my other math class. It's like you have like the table or whatever, but like you don't plug it in. Like you go to it and you change the intervals. So how do I do that? Do you know what I'm talking about?
Potentially.
So it will go by like 1 point.
Yeah, so that would be like the delta table. I think the delta table there. So if you want to make it go from like 0.5 or like count by 0.1s or something like that, then that would be the delta table. The problem is though, we're not really counting by like a regular interval, so that's why I don't show it to you guys with that. But yes, for your other class, that's how you do it. Yeah. So second, window button. So right there, because you get a table set up, and then you want to change your independent variable from automatically being filled in to have it ask you to fill it in. And now if you go to your table, you should already get it. So yeah, that. You can write over top or hit the delete button, and you'll get rid of them that way too. Oh, okay. So what that means then is we have to quit and go to the window button there. And so your window button is so min is negative 10, max is 10. That's fine. But here your y min is 10 and your y max is 10. That's not going to work because that means you're calculating a graph anything. So just oh well, there you go. So now. Yep. And then zoom 6 puts you back to that default. Like you do zoom 6, it takes you to negative 10 to 10, negative 10 to 10. Okay, let me see here. Okay, no, you typed it in correctly. So let's see. Negative 0.1. Were you typing, did you use the minus sign or the negative symbol there? If you didn't use the negative, you might have been using like the minus sign or something like that. That might be it. Yeah, you gotta use the negative button. Negative button. All right. So, yes, right, okay. Looks like we are approaching 2 here, right? Both from the left and from the right. In fact, this one value right here, it's so close it doesn't even like show any difference, right? It gives us 2.000. Now, of course, if we actually like looked at that value, it would probably be still off by a little bit, but it's so close that the calculator doesn't even.
Mine says 2.0005.
Okay, so there you go. So it still is off a little bit, which makes sense. So we can say then for sure that the limit as x approaches 0 of x over square root of x plus 1 minus 1 is equal to 2. Okay, so there's our answer. Later, we will learn how to evaluate this limit by hand without a calculator. Okay, but not right now.
Not now. You gotta wait for that.
That's right. Hold your horses. Okay, so do you want to talk me through this real quick?
We're going to do this one, and this one.
All these right here today.
Yeah, this one first.
Oh, this one first.
And this one. And this is our task for Tuesday. Or Monday. That's the thing with the
Okay,
computer.
so
That's our
today. Okay, so both today.
Yeah, or as much as you get through on the
How
second.
much you get through, and then tomorrow.
Definitely that one on Monday.
Okay. All right. Wonderful. Thank you, Mr. Goff. Okay, so let's continue on here. Got a few more things I'd like to show you, and this idea about limits. So I mentioned that this is one of a couple methods that we'll be using to evaluate limits, or one of the couple like ways that we'll use to evaluate limits. Okay, so there are 3 main approaches that we're going to use to find limits. All right, so what we just did is called the numeric approach, okay, which is just like, you can think of it as like a table of values, okay. Kind of limited in a sense because you need to have a calculator in some sense, or you have to do like a lot of arithmetic by hand, right? So it's kind of limiting in that sense, but we can do it with pretty much any function though. Right? Any function we come across, or anything, any kind of thing we see that we can type into our calculator, we can do it, right? So that's one nice thing, is like anything we see, we can find a limit of, potentially, right? The second method we're going to use, and that's not today. I think we'll hold off on that till tomorrow, at least I want to say. Tomorrow. Yeah, so we'll have you guys come in. All right, that'll be great. All right, but seriously, yeah, we'll but later. So Monday, I guess, the next day of school. All right. Then the final one is the one that is, you know, maybe more familiar to a typical math class, right? Where what you do, right? Like the work you do to come up with a limit. And so we're going to look at this today, okay, as well, in the next thing. And the analytic approach can involve algebra. We know algebra, so we can do it, right? Or it can involve calculus. We don't know calculus, so we won't be able to do that, okay? Okay. If you ever hear one of your friends in like calculus talking about like L'Hopital's rule, that's the calculus way of evaluating a limit. Okay. Note, I just want to make a little note here, nota bene. 1 and 2, okay, are methods of approximating a limit. Okay, so 1 and 2, we're really getting an approximation there. Now, I can tell you, well, the answers that we got to those 2 functions whose limits we found, right? Those answers, those are the answers. They are the limits, okay? But there are other situations where, yeah, when you use the numeric and the graphic approach, it is really just a method of approximating. So let's talk then about that third method, evaluating limits analytically. Okay, and we'll keep it very simple today with the analytic method. Okay, keep it very simple for us. So in some cases, the limit can be evaluated by using direct substitution. Okay? And this is where students can get a little bit, this is where like things can get a little bit cloudy or confusing. Well, if they haven't already, maybe they have already, forgive me, but that can happen there too, other places. But this is where it can get a little confusing. What I mean by this, okay, so what this is saying is the limit as x approaches c of a function equals f of c. Okay, that's a direct substitution. Sometimes you can find the limit by just plugging what you're approaching into the function and evaluating it, okay? This is only true if and only if f is continuous. Okay, this is only true if f is continuous at c. Okay. So if you know your function is everywhere continuous, Mr. Wade, what does continuous mean? Well, remember we talked about like domain restrictions and things. So like if it's a place where you can't divide by zero, like where you're potentially going to divide by zero, that's not continuous there, right? Square root of a negative, it's going to be imaginary, so we would say it's not continuous there either, okay, as well. So think about those domain restrictions, right? Those are places where we're not continuous. Also, if you're talking about like a piecewise function, and if your piecewise function parts don't join up, there's a discontinuity there. There's like a jump, between the two parts of your piecewise function. Okay, stuff like that. So in those cases, you can't just evaluate the limit by direct substitution necessarily. Okay, but where the function is continuous, where it's nice and smooth, you can evaluate the limit just by plugging in. Okay. So, here's an example. Let's evaluate the given limits. So, first example here, the limit as x approaches negative 4 of x. What will be the limit as x approaches negative 4 of x? Negative 4. Okay. Is x as a function ever discontinuous? No. What is x? If we graph it, what does it look like? It's a line. Okay, never is discontinuous, so we can plug that negative 4 in, no problem, we get our answer. All right, let's try another one. Simeon, this goes to A100. I am A101. I think that's Mr. Thompson's room next door. Okay. So, okay. X squared. It's a function. Is it ever discontinuous? No. It's a parabola, right? So then we can just direct substitute here. Is the limit as x approaches, what's the limit as x approaches 3 of x squared? 9. Okay. Thank you, Cindy. Okay, gotcha. The limit as x approaches 2 of 3. Is 3 a function? No. What would the function 3 look like? Yeah, it's a horizontal line, right? It's just a horizontal line that goes through 3, okay? Is a horizontal line ever discontinuous? No. And so what is the limit as x approaches 2 of 3? It's 3, right? There's no place to plug the 2 in. It's just always going to be 3. One more here, and then I'll have you guys try one. The limit is x approaches 2 of x squared plus x minus 6 all over x minus 2. Okay, so it could factor here, but the question I'm going to ask though is, okay, since we're taking a limit here, and we want to try and do direct substitution, is this function, whose limit we're trying to find, is this function continuous everywhere? No. Where is it discontinuous? At 2. Uh-oh. So can we use direct substitution with this function? No. No. But, Ro, you said the numerator factors, right? And it does, okay? So the numerator is going to factor to be x plus 3, x minus 2 over x minus 2. Okay? Yes, you still need to write the limit. Okay? Just like I still have to write the division symbol here, you know, that fraction bar, because I haven't done the division yet. I need to continue to write the limit because I haven't taken the limit yet. All I've done is just rewrite the function. Okay, so this is saying I still have something I need to do. When you drop that limit, you're saying I've done that thing. And we have not done that thing. We have not evaluated the limit as x approaches 2 yet. Okay, now what can we do at this point? Cancel these out, and we're left with the limit as x approaches 2 of x plus 3. Okay. Now, the key thing here, and there's a theorem here that I'm going to show you in a little bit, but I don't have it pulled up just yet here. I wanted to do that. I forgot. I didn't do it in the past year, but I'll do it here now. These two functions, are they identical? No. They agree at all but one point, right? This function, x squared plus x minus 6, all over x minus 2, this is the same as this everywhere except when x is what? 2. Okay? So there's a theorem, I think it's called like two functions that agree at all but one, or functions that agree at all but one point theorem or something like that. But basically the idea is that if you have two functions that are exactly the same except at one point, their limits will be exactly the same everywhere. Okay, so even though these two functions disagree at a single point, at 2, their limits will be the same. Because think about it, if they disagree at just a single point, the behavior as you approach that single point will still be the same, because those are other points where they still agree. So they're going to agree at all but that point. And so the limit behavior of this will be the same as the limit behavior of this. And so we can evaluate the limit of this, and it'll still be the limit of this. What is the limit of this thing as x approaches 2? 5. And so the limit of this thing as x approaches 2 will also be 5. If you don't believe me, type it in your calculator, approach 2 from the left and from the right, and you'll see it goes to 5. Okay? I'm not going to bother showing that theorem, I think. But that is the idea there. These functions agree at all but one point. Their limits will still be the same. Okay? Their limits will still be the same, though. All right, here's one for y'all to try. The limit as x approaches 1 of x squared minus 1 over x minus 1. Okay. You can choose to do it with analytically, or you can choose to do table if you want to. Your choice there. Table or analytically. Numeric or analytic. table, remember you really, to show a full analysis, you need to both approach one from the left and one from the right there, okay? Make sure you're approaching from both sides, okay? Yeah, we'll talk about what happens if your left and right hand sides disagree later. Remember this semi?
Yeah.
Back in the day?
Back in the day. All right, let's take a look here.
Should have gotten 2. 2, 2, 2. Okay. 2. All right. So that's all I've got for you. Any questions on that? All right. So, well, got a lot in here. Your homework is in Google Classroom. I have it posted up here too, so you can record it down right now. Oh, it was up. I guess. Oh, that's right. I know what happened. I'll put it back up here.